Today we're going to spend a little bit of time working with motion problems, and in particular we're going to be talking about a particle moving along a graph. And when we talk about a particle moving along a graph, it's going to kind of bounce back and forth. It's going to go left, then maybe come right, and then come left again, and maybe go right and left. So this particle is going to move along an axis, and we normally move along the x-axis. We start at some value and we just move back and forth, and we show that with kind of a stair-stepping of what the particle is doing. So an example of that would be x of t equals 2t to the third minus 21t squared plus 60t plus 3. And what I want to do is go ahead and kind of plot out what that's going to look like. So on a number line, the first thing we're going to do is go ahead and find what happens at t0. Well, what's happening at t0? If I plug 0 in to these values, I'm going to end up with the value of 3. So I get the point 0, 3. So at time 0, I'm at the point 3. So on my number line, say we start here at 0, and then we have it 3. So at time 0, we start here. And then we can go ahead and look at maybe time 1. At time 1, if you plug 1 into that value, and we can do this into the calculator pretty quickly, I guess. Go to your y equals, go ahead and clear out your y. 2x to the third minus 21x squared plus 60x. Remember that x's and t's doesn't matter, it's all just a variable. So if we do our table setup, make sure we're going a independent variable of ask. Typing in your 0, we get our 3. Typing in 1, we get it at 44. So we get the point 1, 44. So at time 1, we're way out here, maybe at 44. So to chart that, we would go from here to 3 to 44. At time 2, if we type 2 into our calculator, we end up with time 2 is going to give us 55. So we're going to continue out here, maybe to 55. And then time 3, we're going to end up with 48. So at 55, we're coming back now. I guess I should go ahead and time 1, there's time 2. So I'm going to reverse. So I was coming to the right. Now I'm going to go back to the left to 48. And that's at time t3. If I look at, x of 1, 2, 3. It doesn't matter with the variables again. I guess time was 1, 2, and 3. At time 4, we're going to see we're at 45, or at 35, sorry, at 35. So we're going to continue back a little bit more here to 35. And that's at time 4. At time 5, we end up with 28. So again, we're coming back even farther, maybe here to 28, and that's going to be at time 5. At time 6, we're going to be at 39. So at time 6, now again, we were going left, now we're coming back. So we come up, and we're coming back to 39. And we're going to continue this on and on and on. Time 6, now we can go to time 7. I guess I can go ahead and put that in. X of 6. At time 7, we're going to go ahead and get, what do we get? If I plug in 7, I get 80. So I'm going to be way out here. And then we should hopefully see that as, that was just 7 there, as time gets larger and larger and larger, that 2t to the third from our horizontal asymptotes, that's going to take over what this polynomial is doing. So we're going to see that this is going to continue on out. You can plug in some more numbers if you want to see that value. But what I want to see and show is, notice we've come to the left, or come to the right, then we went to the left, and then we came back to the right. So several different things have happened there. And a couple of things I want to talk about. The first thing I want to do is go ahead and find the velocity. So if we talk about the velocity here of this particle, I'm looking at the derivative of the function of its position. So that gives me 6t squared minus 42t plus 60. And what I want to do is go ahead and set that equal to 0. If I'm able to set that equal to 0, We can go ahead and factor out your 6. So we get t squared minus 7t plus 10 equal to 0. Factor that out, we get t minus 7, or t minus 5, t minus 2. That gives our negative 7 for our middle term. So we see that t equals 5 and t equals 2. Since t equals 5 and t equals 2 equals our zeros, notice what happened at time t equals 2 and time t equals 5. So I'm going to go ahead and maybe draw in some dotted lines there to show maybe a little bit of what's happening there. So notice once we hit 0, we changed our position. So we went from left to right, and then at 5 we went from we went going to the right to the left, and then left to the right. So important points there. We see that when the velocity was equal to 0, then our particle changed direction. Something else that I'd like to see is go ahead and set up an interval chart. And we're going to get into these interval charts in the next chapter. But if we start at time 0 and go to 2, and then 2 to 5, and then 5 to infinity, which these we also did talk about in pre-calculus, if I look at the sign of my velocity between 0 and 2, so if I were to plug in a number between 0 and 2, say 1, if I plugged in 1, I have a positive, this in here would be a negative, and this in here would be a negative when t equals 1. So 1 minus 5 gives us negative 4, 1 minus 2 gives you negative 1. So that would give me a positive value. Between 2 and 5, we'll say 3, here I would get a negative value, and here I get a positive value. So I multiply a negative times a positive gives me a negative value. And between 5 and infinity, maybe plug in 6, I get a positive and a positive times a positive, I get a positive. So notice there are velocities on this interval from 0 to 2 are positive. Well, what do we notice between time 0 and time 2? That we were moving in the right direction. We were moving from left to right. Between 2 and 5, we were moving from right to left. And then from 5 to infinity, again, we're going from left to right. So we were moving forwards, and then backwards, and then forwards again. So a positive value is telling us that our particle is moving to the right. A negative value tells us it's moving to the left, and so on and so forth. Something else that I kind of want to talk about is how far have we traveled? So between 0 and 2, we've traveled 52 units along the number line. If we look at the displacement, remember is how far we are from where we began, that's also equal to 52 on the first 2 seconds. But if I come up here to time 3, here at time 3, I was at 48. So my displacement would have been 45. But my distance traveled, I would have gone from 3 up to 55, so I would have traveled 52 units and then back 7 units. So I would have traveled 59 units. So what we're going to see is that the absolute value of my displacement added together is going to give me my total distance traveled. Hopefully that makes a little bit of sense. I'll say it again here. So if we find the displacement, we're looking from the position that we start, how far are we out to that point in time. So at time t equals 4, we're here at 35. So we went from 3 to 35. Our displacement is only 32 units. But we know that we've gone 52 units and then back 20 units. So our distance traveled would be 55 or 52 plus 20, or 72. So that gives you an idea of what we have there. I went ahead and wrote out what hopefully we see there in words. So if our velocity is negative, then our movement is going to be to the left. If it's positive, we move it to the right. Something we didn't talk about is acceleration in there. If velocity and acceleration have the same sign, then we're going to see a speeding up, or our speed increasing. So if you think about velocity being positive and acceleration being positive, so if velocity is being positive, I'm moving in the right direction. And if acceleration is positive, moving in that right direction, we're pushing this push. So if I push a push, then that's going to be speeding up really quick. But if they're different signs, so maybe one's positive, one's negative. So if I'm pushing there, but then my negative is going in the other direction, so it's kind of going to hold this guy back. So we got two forces working against each other, and that's going to be slowing down something, or speed is going to be decreasing. If the velocity is 0 and acceleration is not 0, then we are having a change in direction. And again, our distance, the sum of the absolute values of our displacement, is our distance traveled. So, can we find if the position of a particle is given at time t by s of t equals 2x squared, I guess those should be t's, couldn't they? Time. Find the velocity and acceleration at time 2. So our velocity is the derivative of the position. Our derivative in this case is 6t squared plus 8t. I can go ahead and find then my velocity at time 2. Going ahead and plugging in my 2 there, and we end up with 40. I can find my acceleration, a of t, or the derivative of my velocity, which is the second derivative of position. Again, you don't need to write those, just kind of giving you that kind of a reminder of what acceleration and velocity that relationship is. So we get 12t plus 8. So our acceleration at time 2 is going to be 32. And that'll give us our acceleration and our velocity. Another example. Position of a particle is given by the function. Is the particle speeding up, slowing down, or stationary? Or when is it speeding up, slowing down, or stationary? So the first thing we got to do is go ahead and find our velocity. Our velocity in this case is 6t squared minus 42t plus 60. That looks familiar from somewhere, doesn't it now? So if I go ahead and set that equal to 0, I'm going to go ahead and factor out a 6. So I get t squared minus 7t plus 10 equal to 0. So we get t minus 2 and t minus 5 equal to 0. So t equals 2 and 5. That's my velocity. So it tells me where my function is, or my particle is changing direction. So what I need to do then is go ahead and look at my intervals, which we did. We have 0 to 2, 2 to 5, and 5 to infinity. If I pull back that original paper, so we don't have to redo all of that, we've got, remember, a positive, a negative, and a positive. So this was our v of t. If we go ahead and look at our acceleration, a of t, we'll try to squeeze it in there, we get 12t minus 42. Setting that equal to 0, we're going to add our 42 and divide by 12. 42 divided by 12 gives us 3.5. So with our acceleration, now we're going to look at our intervals 0 to 3.5, and then 3.5 to infinity. Plug in a number between 0 and 3.5. We're going to check 1. Again, it doesn't matter what value we pick as long as it's on an interval. And 3.5 to infinity. Pick a nice number, maybe 5. If I plug that in, I have a negative. If I plug in 5, I end up with a positive. So for a particle to be speeding up, then our velocity and our acceleration have to be going in the same direction. So they have to be positive, positive, or negative, negative. So if we look here, from 0 to 3.5, we're at negative for our acceleration. Our velocity changes from positive to negative at that value of 2. So I know from 2 to 3.5, this particle has the same sign. So if they have the same sign, I know I'm speeding up. Likewise, from 5 to infinity, I have the same sign. They're both positive. So I can put a union there, 5 to infinity. Now when is it going to be slowing down? Well, this is going to be slowing down when they have opposite signs. So here from 0 to 2 it's positive, 0 to 3.5 is negative, so from 0 to 2 these two have different values, positive and negative. We also know from 3.5 to 5. So from 2 to 5 is negative, from 3.5 to infinity is positive. So from 3.5 to 5, those two values are going to be different as well. So we know that they're going to be slowing down. Well, when is this function going to be stationary? Well, the function is going to be stationary by definition. It's stationary when the velocity equals 0 and acceleration is not 0. So our velocity was 0 at times 2 and 5. Our acceleration is 0 at 3.5. So it's not, or it's going to be 0 at 2.5 and 5, but our acceleration is not going to be 0 at that point in time. So we know it's stationary at times t equals 2 and 5. And this could be seconds, minutes, whatever their value is going to be. Our last example here, the position of a particle is given. Find the velocity and acceleration of the functions. So I can go ahead and find those. V of t, 3t squared minus 24t plus 36. And our velocity, a of t, and it's going to give us 6t minus 24. Part B says, when is the particle moving to the left or to the right? So it's moving to the left, we're going to have a negative value. Moving to the right, we're going to have a positive value for v of t. So we're going to take that v of t and set it equal to 0 to start. So we're going to take 3t squared minus 24t plus 36. Setting equals 0, we can go ahead and factor out a 3. And factor out what we got left there. T minus 6, t minus 2 equals 0. So t equals 2 and t equals 6. What I'm interested then is we're larger than 0, so we're going to go from 0 to 2, setting up that interval chart, 2 to 6, and 6 to infinity. I'm going to take a test value between 0 and 2, between 2 and 6, and 6 and infinity. I'm going to go ahead and plug those in to see if I get a positive or a negative value. If I plug in 1, I get 1 minus 6, it gives me a negative, times a negative, so it's positive. Plugging in 3, I end up with a negative times a positive, or a negative, and 7 gives me a positive times a positive. So I'm moving to the right on the interval 0 to 2 union 6 to infinity. Left from 2 to 6. Then it asks us, when is the particle speeding up, slowing down, or stationary? So again, another problem like we had before. We set our acceleration equal to 0, so 6t minus 24, so we get t equals 4 as being our critical value from our acceleration. So we're going from 0 to 4 and then 4 to infinity. We're going to go ahead and test the value, maybe 1 and 5. Plug in 1, I get a negative value. 5, I get a positive value. So again, we're interested in at what values are they the same. Well, I'm negative from 0 to 4 and also from 2 to 6. So those are going to overlap on 2 to 4. I'm also positive from 6 to infinity and 4 to infinity. So they're going to overlap from 6 to infinity. So I'm going to be speeding up on those intervals. Speeding up. Slowing down is when my signs are different. So from 0 to 2, I'm positive. 0 to 4, I'm negative. So those are going to overlap from 0 to 2. They're also going to be opposite signs. I know 2 to 6, I'm negative. 4 to infinity, I'm positive. So I know I'm going to overlap those from 4 to 6. So those don't overlap from 4 to 6 there. So we know that they are going to be slowing down. Stationary is when my velocity equals 0, but my acceleration doesn't. since my velocity equals 2 and 6, or my times 2 and 6 are going to be my zeros and my velocity, neither one of those occur in my acceleration being 0. So we're stationary at time t equals 2 and 6. And hopefully it gives you an idea of some of our motion problems and a particle moving along the axis. Good luck and enjoy!